Okay, so here I will explain Riemann sums and then show how to convert them, and then show how to convert between integrals and then Riemann sums. Okay, so a Riemann sum is basically you have your summation symbol, and then usually your index of summation starts at 1. And then I use this index of summation as I. There's a bunch of different ways you can put it. Some people would use K, but I prefer I because I stands for index. And then your index of summation will stop at a specific number, which is like n. So what this means is if you have if you have a summation of, let's say I, and then you need to set n to a number, let's say n is 5, this summation will equal 1, because it starts at 1, and then you go up by, the index of summation goes up by 1 every time. So it's 1 plus 2 plus 3 plus 4, and then you stop when I equals 5, okay? Let's say you have a different summation. If you want it to be, let's do something a bit more complex, plus I, okay, so it's going to be x plus I squared. And then, so every summation will have an x in it. Okay, so the first one, where I equals 1, it will be x plus 1 squared. And then it's going to be plus x plus, x plus 2 squared. And it's going to be x plus 3 squared. It's going to be x plus 4 squared, as well as x plus 5 squared. And then you can add those up. It would be like 1, 4, 9, 16, and 25. And you add up all these numbers, and it's going to be like 5x plus some number, which is, I can add up for you. It's going to be 30, 55, right? So this equals 5x plus 55, I think. The math might be wrong. It's going to be 10 plus 20 plus 25. Yeah, it's going to be 55. So this summation right here, where you have x plus I squared, is going to be 5x plus 55. Okay, so let's delete all that. Okay, let's not delete that all then. Okay, so that's how summations work. So the only thing missing from the summation is some sort of thing with I in it that will change with each when I increases. And let's look at this guy real quick. So Riemann sums is approximating what the area under the curve will be. So let's say this point is x equals 0, and this point is x equals 4. And then if all these widths are equal, that would have to mean that this is x equals 1, this would be 2, this would be 3, and that would be 4. Okay? So, and then let's say this random function is f of x. And then if we want to find the exact area under the curve, it will be the integral from 0 to 4 of f of x, right? That's going to be the exact area under the curve, this blue shaded in area. But if you want to do a Riemann sum, it won't be an exact area, because it's missing this area, it's missing this, it's missing this, and it's missing this, right? So as you can see, the widths of each rectangle have to be the same, which will be represented by delta x. And then for this, the widths of each rectangle are going to be 1. Okay. So for a Riemann sum, you're always going to have delta x in there. Okay. And then you need some sort of thing to represent the height. The height of the rectangle, because you are adding up you're adding up the areas of every single rectangle here. So this rectangle, area of this rectangle, this rectangle, this rectangle, and then this rectangle. So area, of course, is width times height, and then width is going to be delta x. So the only thing changing is height. And then, as you know, if you have, let's plug in some arbitrary values for h. You have delta x 2 plus delta x 4 plus delta x 8. You can factor out the delta x to be 2 plus 4 plus 8, right? So this is why you can just have delta x here outside of the heights. And then the height is going to be the one that changes with the index of summation. And then you can just find some sort of representation for the height of each rectangle. Okay, so as you can see, if you want to find the height of this rectangle right here, it matches the height at this point of the function. And this point is as of x value of 0, and then you plug the 0 into f of x, which would just be f of x at point 0, which is going to be the this point. So this rectangle has a height of f of 0. This rectangle will have a height of f of 1, because the point at x equals 1 is here, and then matches the height of the rectangle. And then this will be f of 2, f of 3. And then at x of 4, there's no rectangle. You'd only include f of 4 if you're doing right Riemann sums. This is a left Riemann sum, because you're using the value of the function at the left of the rectangle. If you wanted to use right Riemann sums, that would be here. Because see, you set the height of the rectangle at the right point of the rectangle. And then, actually, I can just duplicate this. You see, you set it at the right point of the rectangle. That. And then that would be a right Riemann sum. I can change the color of that for you guys, actually. Set it to green. So if you look at the right Riemann sum, this point, f equals 0, is not used as a height for any of the rectangles. But right now we're doing a left Riemann sum. So when you're doing summations, you won't be able to manually plug in these x values right here. So what you do is, this is going to be left bound at 0, right? You know that the left bound is 0. And then it's going to be plus the width of the triangle multiplied by some integer, right? And you can say that because you start at the left bound, and then to find the height of this rectangle right here, you start at the left bound. So I will start at 0. And then to find the height at the second rectangle, you can set I equals 1 for the second rectangle. It's a bit intuitive. I mean, it's a bit like convoluted. I will start from 1 to 2 to 3 to 4. It's a bit like coding. Instead of it starting at 1, it starts from 0. So n will equal the number of which rectangle it is, and then I will equal whatever value you have to plug in. So you have 0 for the left bound, and then for the first rectangle, you can see that you plug in 0 for I, and then for x will equal 1, because that's the height, that's the width that we have for the rectangles. Okay. And then it'll be 1 plus 1 times 0, which equals 0, which, doesn't equal 0. Yeah, it does equal 0. Equals 0. And then that 0 is going to be what's plugged into the function to find the y value. And then if you want to find the the first rectangle, I apologize, the second rectangle, which you need to plug in I equals 1, you're going to do 0 plus 1 times 1, because delta x will always equal 1 for this scenario, because that's going to be the width that we're going to use. So equals 1, it's going to be f1, okay? And then if you want to do the third rectangle, it's going to be 0 plus 1 times 2, right? That equals, which matches this. And then this will work for other stuff as well. If you want to change values, let's say this is, let's say this is 100, this is 50, this is 25, this is 75. So you can see that the new width of the rectangle, this will now be, this will now be 100. It's then from 0 to 100. Fuck's sake. Okay. So you can now see that the width of each rectangle is 25. And then you can look at this thing again. I'm gonna rewrite it down here. The number of the rectangle, 2, 3, 4, will correspond to this index you're going to use. So 0, 1, 2, 3. And you can have the same formula, the left bound, which is 0. If this was at x equals like 5 or something, this value right here would be 5, not 0, but it is 0 for this scenario. And it's going to be delta x times I. So it's going to be 0 plus 25 times the number that will change I. So to find the height of the first rectangle right here, you're going to want to plug in first rectangle. You're going to want to plug in 0 for I. So it's going to be f0 plus 0, f0. So to find the height, you plug in 0 to f. And then to find the second rectangle, you're going to want to plug in 1 for I. It's going to be 0 plus 25 times 1 equals f25, right? So this new point, this new height will be f of 25. And then to find the height of the fourth rectangle, we'll skip the third one because you should get it. Fourth rectangle, that's going to be 0 plus 25 times, it's going to be 3, right? Because, 3, because the fourth rectangle corresponds to 3. It's number 3. And this will equal f75, right? And that makes sense because if you look at the fourth rectangle, you want to check the height is f at 75. This is the fourth rectangle. And then this height matches this point. And this point at x is at the point. Okay. that is what, so you can find out what to plug in here. It's going to be okay. So A is going to be the lower bound, and then the delta x will be your change in x, the width of each rectangle, and this I will be this index of summation. So something that will be given to you is like, you're only going to want to plug in stuff for here and here. This I will remain there the entire time. For every single scenario, you'll have an I, because this I changes because of the summation, not because of the scenario. And this N switches for different things. And then just erase all this. Let's say we want to do a right Riemann sum. I'll give you a quick example. I only do 2 rectangles for this time. And then let's set this at x equals 0 again. This will be 25 and 50. This time, the I will match the number of rectangles. So for the left Riemann sum, it would have been 1, 0, 1, 2, and 3. But for the right Riemann sum, it's going to be 1, 2, and 3, and 4. So if you have with the lower bound being 0, and then you have 25 as the width. If you want to find the height of the first rectangle, you just plug in 1 for I. It's going to be f of 25, which matches here. You plug in 25 to the function to get the height of the first rectangle. Okay. So by looking at this, you can tell that this is a right Riemann sum because it starts at I equals 1. If it was I equals 0, then this would be a left Riemann sum. And then there are also problems where you don't know where the width of the triangle, the width of the rectangles aren't given to you. So you have, let's say this is going to be 0, and then we'll set this at point 100. And you don't know you don't know what n is, the number of rectangles, and then you also don't know what x is. Well, you know one of them, but you need to be able to find. You need to be able to find the other one by knowing only one. And then the formula for that is where delta x is the width of the rectangles, n is the number of rectangles, and then b is the upper bound, a is the lower bound. So for this scenario, b is 100, a is 0. And then let's just use the scenario that's in the picture with 4 rectangles. You're going to have delta x equals 100 minus a equals 4. And you find that the width of each rectangle is 25. If you wanted to split it into 10 rectangles, you find that the width of each one is 10. Okay. If you want there to be just one rectangle, the width of that would be 100. And then that would look something like this. It would depend on which type of Riemann sum you want. If you want, this is a really, really bad approximation, by the way. So just to understand the concept, this will be a left Riemann sum, this will be a right Riemann sum, where you only have one rectangle for the entire approximation. So actually, let's keep that there. If you have one triangle, you see that you're missing out on all the space right here in your approximation. So that's going to be a really, really bad approximation. And then if you look at the one with 4 rectangles, you see that there's going to be much less space missed, which makes it a much better approximation. So you can derive that the greater number of triangles there are, the more accurate the Riemann sum will be. And then here you can see that delta x and n are inversely proportional. So you want n to increase for more accuracy. So n will increase, and then if n increases, delta x has to decrease. Okay. So you'll see something that looks like this. Limit of n to infinity. Okay. So this means that you can have an infinite number of rectangles, and then each will have a width of 0. It'll approach 0 as n approaches infinity. So that's going to be a basically perfect approximation of this area right here. And then you know this formula right here. Let's bring it over. You want to find okay. So this is what we have right here. So I'm going to copy all this and then apply it to a scenario. So we know all this, we want to find this. So here, well, if you have a limit to infinity, the left or right Riemann sum doesn't really matter. But if you have like a finite number of rectangles, then you will want to look at this index. But when you have this guy, I doesn't really matter what it starts at. I'm trying to copy this image. Okay, what we want to do is compare it with what we have. Okay, so you can notice that there's something in this parenthesis times this guy, right? And then here you can see some large thing times delta x. So you should be able to derive that 7 over n equals delta x, right? And that matches what we have up here, where delta x equals b minus a over n. These n matches, and then you have 7 equals b minus a, where 7 is the width of the integral. Like let's say you have this random function, and then you want to find this area. This width of the interval will be 7. And then if you want 2 rectangles, n equals 2, you split it into 2 rectangles. You have one rectangle and another rectangle as approximation. And then you have 7 over 2. Each rectangle will have a width of 3.5. Okay? But what we want is an infinite number of rectangles to find a perfect approximation. Okay, so you have so we know what delta x is, and then you just want to find this part right here. And then if you look at the equation given, you can find that there are these repeat things that appear. And then you look at delta x right here, you can see that delta x appears inside the inside each of these repeating, like, I don't know what to call it. These repeating equations, I suppose. And then if you compare it with you can see that if you want to plug in 7 plus 7 over n for delta x, you notice that these two match. 7 over n times I, and then 7 over n plus I, right? So you can cancel these out. Let's do it a bit more formally. These can be cancelled out by like subtracting 7 over n I from each side, which gives you that a equals -3. And you have that 7 equals b minus a. And then a, as you know, is the lower bound, so b has to be higher. So 7 equals b minus a. And then you plug in -3, which will be b minus. It's going to be wait, am I stupid? Oh yeah, wait, no, I'm fine. Okay, so b will equal 4, a will equal -3. So you want to plug in -3 for a, and then 4 for b, and then you just need to find what f of x is, right? And then you look at this guy, and then you compare it to this. And then if you try to find that if f of x equals x squared plus or minus 5x plus 6, right? Because if you just ignore like these highlighted parts, you have something squared minus 5 times something, that same something, plus 6, right? Which matches this. You plug in this formula right here into the x of f of x. So you can find that f of x equals this. And then you can check that like that. If you want to find which will equal you have to plug in this guy right here into every time that x appears into the function, which will be right. And then this matches what appeared here. And then 7 over n matches your delta x. So you have your f of x, you can plug it into here. It's going to be Okay. So let's copy this. And delete this guy. So these two things I think my thing is not having a good time. Okay. These two things are equal.